What's the peak-to-peak voltage of a sine wave that has an RMS voltage of 120 volts? Okay, let's look at the picture. And this is throwing another little curve at us here. But let's start with 120 volts. We have an RMS of 120 volts. That's this one right here, 120 volts AC. Okay. Now, before we can find the peak-to-peak, and the peak-to-peak is from this peak to this peak. Okay. Before we can find that, we have to find this peak. And to find that peak, we're going to take the RMS voltage, and we're going to multiply it by 1.414. So that voltage, the peak voltage there is going to be 169.7 volts. Here's 169.7 volts. The peak-to-peak voltage is twice that. So the distance from here to here is twice 169.7, or 339.4, this answer here. What's the RMS voltage of a sine wave with a value of 17 volts peak? Okay, you've seen the picture. You have you want to know, you have a voltage that has a 17 volt peak, and you want to know what the RMS of it is. See if you can take a look at those various values there and figure out what it is before I give it to you. This one is half of the 17 volts. This one is more than half but less than the 17. This is more than the 17, and this is twice the 17. Which one's it going to be? Okay, it's going to be the 12 volts. The 17 times 0.707 is going to be 12 volts. So you have a 17 volt peak here, and your RMS voltage is 7/10 of that, or 12 volts. What percentage of power loss would result from a transmission line loss of 1 dB? They've thrown a dB in here. I don't know why they put these in the order they do, but this is how they fall. A loss of 1 dB is about a loss of 20%, about a fifth of your power, if you have a transmission line loss of 1 dB. What's the ratio of peak envelope power to average power for an unmodulated carrier? Okay, we're talking here about an radio frequency carrier wave, and this is just almost a definitional thing. The key here is that it is not modulated. So the average power is not varying with any kind of modulation. And the ratio of the peak envelope power to the average power for an unmodulated carrier is 1.0. In other words, they are the same. Peak envelope power is the same as the average power for an unmodulated carrier. Okay? And I can't draw you a picture that will show you that. All I can do is tell you that they are the same as each other. And if you get this question, the answer is 1.0. Okay, what would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? Now, here we're talking about an alternating current. We want to know the RMS voltage, and we have a dummy load that which is the same as a resistor. A dummy load is a resistor, okay, and it's dissipating 1200 watts. Okay. Using a formula from here, the voltage, which is what we're looking for, is the square root of the power times the resistance. We know the power is 1200 watts. We know the resistance is 50 ohms. We multiply the two of those. We take the square root of that, and it's 245 volts. Okay, and we've taken we have found this formula here by looking over here in volts. And we see that volts is equal to the square root of the power times the resistance. Okay, so we took the power, we took the resistance, we multiplied them together, and we found the square root, 245 volts. Okay, What's the output PEP of an unmodulated carrier if an average reading watt meter connected to the transmitter output indicates 1060 watts? Now, what did I tell you the relationship was between an unmodulated carrier and average power? It's a ratio of 1.0, isn't it? It's the same thing. So your 160 watts on your average reading watt meter means you have an unmodulated carrier of 1060 watts. Okay, here we are at number 6 now. You have some additional ammunition in your arsenal here to deal with this question. What's the output PEP from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter output? Okay, let's take a look at what we're going to have to do here. We need to find the RMS. To do watts, we have to find the RMS voltage. And to find the RMS voltage, we have to go from the 200 peak to peak. We have to take it to 100 peak. Okay? And with 100 peak, we know that we multiply that times 0.707. So our RMS voltage is 70.7. Okay, we can get our power formula here. To do that, we can look over here and we can see power in watts is equal to the voltage squared divided by the resistance, because those are the values that we have here, is the voltage and the resistance. So we square the voltages, 70.7 times 70.7. We divide that by the 50 ohms. That gives us 4998 divided by 50, which is 99.96, which is really close to 100 watts. Okay, here's a similar question with just different values to it. In fact, it's an identical question with different values. Okay, we're going to do the same thing. This time we have 500 volts peak to peak. And so the peak will be 250, half of the peak to peak, 250. We take the 250 volts, we multiply it by 0.707, and we have RMS voltage of 177. Okay? And we use that same formula. Power is equal to the square of the voltage divided by the resistance. So we have 177 times 177 divided by 50. That equals 31,329 divided by 50, which is 626.58, which is real close to 625 watts.